Okay, since A is much smaller than X and A much smaller than D, so you can see this term, you can say 1 minus D minus A is roughly 1 over D. Agree? Because yeah, big number minus a small number, you can say, okay, it's similar to almost 1 minus D, but the rest is still the same. So then you can see I can combine this into one term. 2 pi 1 over A, okay, minus 1 over X plus 1 over D minus X minus 1 over D. Agree?
Yeah.
Okay. Okay, now we're going to bring did you notice something?
What kind of thing?
You notice the first term? Okay, I can do this. I can do this. I can do this. I rho over 2 pi A, right? Correct?
Yeah.
I can say plus, right? I rho over 2 pi. I can put 1 minus D minus X minus 1 over X minus 1 over D. Agree?
Yes.
Okay, so if you look at this, did you notice something familiar? Okay, yes, something familiar. Okay, you haven't seen. Do you notice this term? What's that?
This is VE.
No, rho over 2 pi A. What is rho over 2 pi A?
R, resistance.
Actually, R of the hemisphere, right?
Yeah.
Yes. So this is R of the hemisphere. Okay, if I bring I to the other side, I will get VEP over I. Okay? Then I will left with R hemisphere plus 1 over 2 pi 1 minus D minus X minus 1 over X minus 1 over D. Correct? Correct or not? Oh, rho. Should be rho, yeah? Okay. All right. Now, you see,
yeah, correct.
you see, this is R hemisphere. This is actually R through. Correct?
Yeah.
And the whole thing is actually R measured. This is R measured. Because this is what we measure, right? VE divided by I. So you see, R measured is equal to R2 only and only if what?
X equal to 0.62.
No, that one is the solution from this equation. Can you see the equation?
Oh, okay. If
Rho over 2 pi.
if
What?
yeah, equal to 0.
Go to 0.
Yeah, this whole term equal to
Okay, now you solve this. I'll give you 15 minutes. Okay, you see, so that equation is equal to this, right? Correct?
correct.
So x d. So this is equal to x d minus d minus x d minus x d minus x equal to 0, correct? Yes? That is xd minus d square plus xd square minus xt plus x square equal to 0. Yes or no?
Okay.
So if you want to make x as variable, let's say d is 1 per unit because d is the longer, or you can leave d there as constant. If you leave d as constant, also okay, but I think we can leave d there as, okay, first solve this one first. Anyway, you can see x square plus x d square x minus d square equal to 0. Correct? Because you cancel these two terms,
Yeah.
this xd and xt. Now, you can leave it like that. Then assuming d as a constant or 1 per unit, if d is assumed to 1, this is for 1 per unit. Then x square plus x minus 1 equal to 0. Correct? Because you can say d is 100%. Okay, 100%. So what is x? Because we just want a fraction, right? X, how many percent of d? Which is 61.8%. So now let's say d equal to 1. Or you can leave d there. It doesn't matter. Leave it as a constant. But you can solve it also just to find the root. Therefore, root of x is equal to?
Oh, okay.
Yes. So you need to find the root of x. Therefore, x has two components equal to what?
Oh, okay.
So if you have ax squared plus bx plus c equal to 0, x is equal to, what's the formula? B squared minus 4ac over 2a, right? Minus b plus minus, because you have two terms. Minus b, correct? Yes. So here, you can solve it. What's the answer?
Okay. Now wait a moment.
Okay, the first one, minus b is minus 1, plus minus b squared, which is 1, 4ac, which is plus 4ac, yes, divide by 2a, which is 2. So you have minus 0.5 plus minus square root 5 over 2. which is, we have two answers.
Mm.
So 2.23 divided by 2, which is 1.118. 1.118. So you either have minus 0.5, which is 0.618, or minus 1.618. Is that answer? Okay.
Yeah.
Therefore, it cannot be negative because it's distance now.
Mm.
Not possible, since distance is positive. So the answer is x is equal to 0.618 multiplied by d, which is 1. So now if you bring it back, is d. So this is the answer. Understand?
Yeah, okay. Can get it.
Yes. So meaning to say, you can get V divided by I, which is the voltage measured divided by current injected, giving a resistance value. Only that resistance is equal to the true resistance only and only if you put your probe P at X and probe C at D from E, and X is equal to 0.618 D. So that's proof the fall-off potential method. If you want to do this in the field, you have to measure, for example, D equal to 100 meters. Then you need to measure 61.8 meters from E for your voltage probe. Then you inject the current. Then you measure whatever resistance measured. That resistance measured is what is the resistance of the probe or the electrode. Okay? This is called fall-off potential method.
Okay.
Okay. So what happened is like this. If you were to, if you want to do measurement, wait, I want to, now, if you want to measure any electrode, let's say this is your electrode, your earthing electrode, is connected to a terminal there. So this is your electrode, maybe you have 3 rods there, and then connected there. Okay, you want to measure this, the resistance of this electrode having a soil resistivity rho. So all you need to do is bring 3 probe. So you just need 2 probe now because one is already at the grounding rod. So you need to put 2 more, one here, one here. Just make sure it's contact with the soil, maybe about 10 cm, or as long as it's firmly in contact. And then you put your current here,